So we're going to start with number 6, with the pirates being chased by the space police, and they're traveling. Now, how many different frames of reference do we have with this problem right now? 3. 3 frames of reference. Guys, remember, you don't have to work along with me, but please keep it down low enough so I can hear myself. There are 3 frames of reference: the space, the police, and the pirates frame of reference. And if we look at it, the pirates' velocity is and the police velocity are both given to us in the frame of reference of the space. And then they give us the distance that they're apart. That would be the same as measured from all frames of reference, so that'd be okay. So which frame of reference do you guys want to approach the problem? In spaces? Okay. That's good, because A-Block did this exact problem, and they did it in the frame of reference of the pirate. So it'll be good. We'll do it in a different frame of reference, and hopefully come up to the same answer. All right? So in the spaces frame of reference, both ships are traveling, and what we're trying to find is how long until they occupy the same space. All right? So let's start with number 6. The line that I would put for this is in space frame of reference. And many times the abbreviation we'll use for that is FOR, with the F and the R capitalized. Both ships are traveling. At constant speeds. And then I'd probably put something like need to be at same place at same time. So they need to be at the same place at the same time. All right. So rather than redrawing it, let me grab it. That's what I'm assuming. So. Alrighty. Why didn't the pirates buy a better ship? You know? Alright, so let's just get some facts down that they tell me. They tell me the pirates are traveling at 1273. So that's this one. That would be my velocity of the pirates with respect to space. It is 1273 kilometers an hour. I'm going to take this direction as positive. Is that okay with everyone? Okay. Then they tell me the police is 1419. So velocity of the police with respect to space is 1419 kilometers an hour. And I believe they tell us that we're 50 kilometers apart, right? 50 kilometers from one another. Okay? So, these two have to be at the same place at the same time. So, if, let's call where the police start We'll call that 0 kilometers. So that would mean here where the pirate starts is 50 kilometers, and where they end up is some place D down here. So for the pirates, both of these, actually, I'm going to just write this one out so I'll make life easier. I'm going to use D equals D naught plus V initial T plus 1/2 AT squared. Oh, but none of them are accelerating. So that's 0 for all of them, right? So we have a constant velocity here, no acceleration at all. All right, so on the pirate side here, I'll use different colors. On the pirate side, we're going to end up at D. The pirates start at 50 kilometers at, in this frame of reference, 1,273 kilometers an hour for some amount of time, T. On the police's side, they're going to end up at D. They start at 0 kilometers, plus 19 kilometers an hour, and move for time T also. Since I'm interested in T, I probably don't want to set one of these equal to D and put it in for the other. Probably don't want to set one of these equal to T and substitute in the other one, because then I'd find D and then have to go back and find T. But I could set one of them equal to D and put it into, oh wait a minute, they're both equal to D. Oh, so I can just say 50 kilometers plus 12. All right, see you after lunch. I was going to leave it open if someone was in here, and then they could lock it on their way out. You don't know how to solve that?
Well, for T, you put T with that. Am I right?
Yes.
So, you would divide one side by T.
Nope.
No, you would have that one. Oh, okay. What? So, you would...
What she was realizing is that I'm just going to bring the two T terms onto the same side. So have 50 kilometers on one side, and that would be equal the 19 kilometers an hour T minus the 1273 kilometers an hour T. So I'm just getting all the T's on one side, right?
Yep.
That's what you realized.
So then there's two T's.
Well, then I do the algebra. And this is 19 minus 1273. T. Right? Because I group like terms.
No matter which one's first.
Well, I'm going for a positive number. So I'm hoping the bigger one, yeah, it should.
Oh, 158 on that. Divided by 158.
I get a time of 0.3424657534 hours, right? But they want the answer in minutes. So I'm just hours to minutes is times 60, right? And so I get a T of 20.5 minutes. Yeah, they asked for it. They asked for it in minutes. And I get 20.5. And so I'm saying no, they're not going to escape. And yay! All right, so We're going to look at number 2 now. Number 2. Huck Finn walks at this speed across his raft. So he walks perpendicular to the raft's motion relative to the shore. Alright, so, folks, remember, you do not need to follow along with me, but you need to be quiet enough I can hear myself. Alright? Please, thank you. Alright, so, they want to know what his velocity is relative to the riverbank. For this one, I'm going to start off my y by doing a vector diagram here. All right, so this is number 2. The river. River is this way. Oops. I'm doing number 2. Someone asked for it. Get my river this way. His velocity relative velocity of Huck to the water is that way. Velocity of the water relative to the bank is that way. Then, so those two would add together to be the velocity of Huck relative to the riverbank, with this angle being theta. So that would be my y for this one. What I would write, start with equation-wise, and this is actually, it's an example of this on the equation sheet, but it would be the velocity of Huck to the water plus the velocity of the water to the bank is going to equal the velocity of Huck to the bank. So that's my valid physics equation. It's an example of that type of equation right on the equation sheet. Now, I start looking at these, and of course the directionality matters. So let's see, what do they tell me? They tell me Huck to the water. Well, I already took that into consideration, right? In my drawing. But you're right. So I know it's a right triangle, because I could have a non-right triangle. We haven't done any of those because of your math, but we could do. There's nothing restricting us to a right triangle. See, because mine is too. It's Huckberry Finn, and there's a Huck. Oh. And you didn't think Midsummer's Night Dream instead? That was a terrible Shakespeare play? Alright, so his velocity relative to the water, which is his raft. The water and his raft are moving at the same rate, so they tell me that his speed relative to the water or the raft, whichever way you want to think about that, 0.2 meters per second, I think. Yeah. And then the water to the bank is 1.9 meters per second. Notice I'm leaving off the vector sign because these are just the speeds. It doesn't take into account the directionality. I've got to take into account the directionality when I actually do this equation. And the way I take into account the directionality of the magnitudes is by using a squared plus b squared equals c squared. So I've got 0.2 meters per second squared plus 1.9 meters per second squared equals speed of puck with the bank squared. I do that, and I get this speed most common mistake will be to forget to square root your answer. But I get a 1.91 meters per second, the speed relative to the bank. I'm going to take a risk and not put it in. And they want now what angle he's at counterclockwise from the direction of the river current. So I go back up here. The river current is going in that direction, right? This way. Counterclockwise from that would be this angle here that I just drew in black. So it's going to be 90 minus theta, right? Do you guys see that? So what I'm going to do is I'm going to figure out what theta is, and then do 90 minus theta. And theta is, I'm going to use tangent. So I'm going to use that tan of theta equals opposite 1.9 meters per second over adjacent 0.20 meters per second. Therefore, theta is the inverse tan of that. I get a value of theta as, let's see, .833.99099,404 degrees. And I do 90 minus theta because of the angle they asked for. I did that math right there on my calculator. Remember, it's shift tan to get the inverse tan?
Yeah, and then I got 1.5.
You did something incorrect. Can I see what you put into your calculator? I can probably tell you. You're in radians. Remember, hit mode and change back to degrees. Because in here they say counterclockwise from the direction of the river current. So when I set up my diagram, I set up this direction and this being theta from straight across to that being theta. I want this black angle here. That's why I did 90 minus it. If I had set up my triangle differently, I could have solved directly for it. I didn't really look ahead. Let me see if I get the right answers, though. Did you change yours to degrees?
Yeah.
That sounds better. What's it? 1.91 and 6.01.